Hello everyone, and welcome to part 1 of chapter 30, and this will be the final chapter for Physics 213. And in this chapter, basically we're going to see everything from the entire semester come together into this beautiful tapestry of electromagnetic interaction. And we call this interaction electromagnetic induction. And the root word there for induction is to induce or to cause something to happen. And what we're going to see is that we will be able to induce electric current by manipulating magnetic phenomenon within an area. But at the same time, we can also induce magnetic effects by manipulating the electric phenomenon in the area. So the electric and magnetic definitions that we've been covering this semester, they've really been two sides of the same coin this whole time. And we finally get to put everything together into this idea of electromagnetic induction. And so the definitions that come with this chapter are a bit extensive. I figured I'd save us some time just by typing these out before I started the video. So with electromagnetic induction, we have two specific phenomenon that can occur. The first one is that we will see electric current induced in a conductor. So it does have to be some material that can conduct electric charge. And these charges will move, the conductor itself needs to be moving relative to a magnetic field within the area. Now that term of relative means that, I should expand my screen here. That term relative means that we can either have the conducting material itself moving through the magnetic field, or we can take the source of that magnetic field and we can move that. So that term of relative means that there's some motion occurring in the system. And that's been the big driving idea behind how magnetism and electric charge relate to one another, is that charge has to be moving. And so the result is based on how the magnetic field affects the way that those charges move by producing a magnetic force. And we saw the equations for magnetic force back in chapter 28. The second phenomenon that we will see is that there will be a generation of an electric field that is associated with a time-dependent magnetic field. Sorry, there's a typo there. Not filed, field. And that electric field will then induce charge to move through the inductor. So we already know that if we have an electric field, that electric field will produce a force on a charge, and then that force will start to move. And so combining that charge with the motion of the charge, we have current. But the trick is, how do we get this electric field to be generated, or how do we produce that electric field? Well, that's going to come from the magnetic phenomenon that we've been learning about these last two chapters. But the easier thing is to really just jump into the methods of causing this electromagnetic induction. And of the three methods, the way that we can cause induction to occur, one way is that we can change the magnetic field strength that passes through a coil. And so what we can do is we can draw ourselves a coil. And in the previous chapter, this is what we would have called a solenoid. And we know that if we pass a current through the coil, that coil will generate a magnetic field. But that's the electric phenomenon producing the magnetic phenomenon. We now want to go the other way. We want to take a magnetic phenomenon and we want to produce an electric phenomenon. So in order for that to happen, what we need is we need to provide some kind of external magnetic field, pass that magnetic field through the coil, and then that will cause charge to start moving through the conducting material of that coil. In other words, we will see electric current induced within this coil. The question as to which way that current will flow, we'll get to that in a little bit. But the idea behind this is that the strength of that magnetic field, the strength of that external magnetic field needs to be changing in order for us to induce current within that conducting material. And so a change in magnetic field, whether it's with respect to time or with respect to position, in either case, we can probably convert the expression to a time-dependent relationship. But one way to accomplish this would just be to take a magnet and move that magnet closer and further away from that coil. And that is all that we need to induce an electric current within that material. And this idea was very popular about 10 years ago. People were making flashlights that used this concept. There would be a very tightly wound coil of wire inside the flashlight, and then they would have a small magnet, and you would shake the flashlight back and forth, causing that magnet to pass back and forth through that coil, and it would induce electric current. That electric current would then go to a capacitor plate somewhere inside the flashlight and store up charge. And then you could release that charge into the light bulb by flipping a switch, and then you would get some light for maybe about 10 seconds until you've dissipated the capacitor, and then you'd have to shake the flashlight up again. And so it was a very novel idea. It was really cool because you could have a flashlight that would work without needing batteries. All you'd have to do is shake the flashlight up for about 30 seconds, and then you get about 10 seconds worth of light. But obviously not that useful in an emergency situation where you need constant light. But maybe if you were going camping or something, it was a very useful idea. They're kind of expensive though, but you can still buy them different places. But that brings us to the second method for inducing electric current, is that if we change the cross-sectional area through which the magnetic field passes through the coil. Down here we have our external magnetic field passing directly through the coil. And we can take the cross-sectional area of that coil. Let's fill in the we can do better than that. Let's take some purple. There is a cross-sectional area associated with the coil, and we can relate that to an area vector. And as our external magnetic field passes through the coil, there is an angle relationship between our magnetic field vector and the area vector of that coil. So what would happen if we changed the orientation of the magnetic field? What if we changed the direction that that magnetic field was pointing? Well, maybe we have our magnetic field pointing this way. There would be a component of that magnetic field that points in the direction of A, but then there would be a component that points perpendicular to that. And so any changes in the magnitude of the magnetic field as it passes through the coil, well, this is kind of reiterating the first method. If there's a change in the magnetic field strength, well, that can happen if we reorient the magnetic field, or I wouldn't even have to change the magnetic field. I could just rotate the coil itself while it's in that magnetic field, and that would cause a change in the amount of magnetic field that can pass through the coil. And that brings us to the third method. We can change the orientation of how the coil and the magnetic field are lined up. One other thing that I should mention, the actual idea behind this is if we're going to change the cross-sectional area of that coil, another way that we could do that is if we could somehow stretch the coil out. If we could make the radius of the coil larger or smaller than what it currently is, then that would change the amount of magnetic field that could pass through the coil at any given moment. Now, I mentioned here at the very end of the typed notes that all three of these methods have one thing in common. So whether we're changing the magnetic field, or we're changing the cross-sectional area, or if we're changing the orientation, or rather the vector relationship between magnetic field and cross-sectional area, all three of these methods effectively do one thing, and that is that they all cause a change in magnetic flux. Well, what is magnetic flux? It's very similar to the idea of electric flux. Back in chapter 23, we defined electric flux as the amount of electric field that passed through a given surface area. And there was an angle relationship involved. That angle relationship was based on cosine theta, because if we have an electric field that passes through a cross-sectional area, we're going to get the maximum amount of field passing through that area if the two vectors are running parallel to each other. Parallel vectors have an angle relationship of 0. Cosine of 0 is 1. But then if we had an electric field that was running perpendicular to the area vector, well, that's a 90-degree relationship, and so we don't get any field to pass through that surface area. The exact same idea can be used with a magnetic field passing through a cross-sectional area. And that's exactly what we have happening with this coil. We have a magnetic field that we are passing through that coil, and that coil has a cross-sectional area associated with it, and so there is a magnetic flux. If we take our expression for magnetic flux, so we want to make sure that we're specifying the difference between the two, but in this case we have magnetic flux. Our magnetic flux, we can evaluate this the same way that we do with electric flux. There is a cosine relationship. And if we look at the definition of magnetic flux here, well, there are three things that could possibly change. We could change the magnitude of the magnetic field. We could change the magnitude of the cross-sectional area for the loop, or we could change the angle relationship between the two vectors. And so those are the three different methods in which we can use to induce electric current within a conductor. And so we're going to look at these three different methods and see what happens. Now that we have our definition for electric flux, and now that we know that a change in electric flux, so changing any one of these three items can cause induction. So induction is going to be caused by a change in the magnetic flux. So, induction. What do we mean by induction? Well, the end result that we're really looking for is we want to have some amount of induced current within our conducting material. So let's say we do have a coil of wire, and the magnetic flux associated with this wire is changing. In that case, there will be some current generated within this coil, and it doesn't have to be connected to a battery or any kind of EMF source, which is kind of weird because anytime that we've talked about current, like with Ohm's law, we said that there had to be some kind of electric potential to provide the current that passes through the material. And so there will be a resistance associated with the wire that we're using to make this coil. And if we were to update Ohm's law to take into account the use of an EMF, then we just get this expression right here. But we said that there are no batteries in this system. Our coil is not hooked up to anything. It's just the coil. And we have this changing magnetic flux that's associated with the coil. Now, I don't know if we're changing the area or the magnetic field or the angle. All I know is that we're going to be changing the magnetic flux somehow. Okay, we're going to change at least one of those things in the expression, maybe more. But Ohm's law says if you have current in a system, there has to be some kind of a driving force. There has to be some kind of electric potential. And so what we're going to see is that the change in magnetic flux is going to create an electromagnetic force in this coil. And we're going to call this the induced EMF. There will be an electromagnetic force induced in that coil. It's not a physical EMF. Again, there is no physical battery. There's no generator or solar cell or anything like that. The effect is invisible, but it is there. And that is the only way that we are going to be able to produce any kind of current to flow through this coil without physically having a battery connected to it. And so this induced EMF, we're going to use the subscript of capital I to indicate that this is an induced EMF. And so if I have an induced EMF, if I induce an electromagnetic force on this coil, there is a certain amount of resistance associated with that coil. As such, we will produce current that will run through that coil. But we're going to call that current induced current. This is current that is induced in the circuit. And we don't want to get this confused with a regular current, like little I. And so we're going to call induced current capital I. And now we have Ohm's law rewritten for this thing that we call induction. As we change the magnetic flux, we will induce an electromagnetic force, which will in turn induce a current in that conducting material. It just so happens that this conducting material is in the shape of a coil. All right, well, if our induced EMF is going to be produced because we're changing the magnetic flux through that coil, can we put together some kind of an equation that relates the amount of induced EMF to how our magnetic flux is changing? Well, we can change the magnetic flux, but how are we going to change it? Are we going to change it with respect to time? Are we going to change it with respect to some change in position? If this coil is moving, if the coil is rotating, are we going to see it change with respect to that rotation? Well, I think we should limit ourselves to a time dependency. Mainly because in our definition for electromagnetic induction, one of the first things that shows up in our definitions is that we're going to be looking at the changes in magnetic fields with respect to time. And anything that changes can be measured with respect to time. So we'll stick with a time-dependent change in our magnetic flux. But how long is the time interval going to be? Remember, delta t can be very small or it can be very large. And I would much rather have a more exact value of the amount of current that is passing through my circuit at any given time. And that means I need to get a more exact value of the EMF that is causing that current. So we're going to shrink this change in magnetic flux down to an infinitesimal statement. And there is a direct proportionality between the rate at which our magnetic flux changes and the amount of electromagnetic force that is produced. And this relationship is called Faraday's law. So Faraday said that the generation of current within a circuit implies the existence of an EMF. And so we have that right here. If our coil is not connected to a battery, yet we're measuring current passing through it, then there's some invisible electromagnetic force that is occurring. And then Faraday said that this induced EMF is going to be proportional to the change in the magnetic flux. Now, Faraday was really close to having this actually be an equality. But I think he kind of rushed wanting to publish his findings, and he said there's this direct proportionality between the amount of electromagnetic force that we get from our changing magnetic flux, and so that would mean that there would also be a direct proportionality to the amount of induced current that we see. Like I said, if Faraday had just stuck with it a little bit longer, he would have found out what the actual relationship is. But somebody else figured that out. And that other person was Lentz. And so Lentz came up with his own law, which is basically just Faraday's law, except we incorporate one extra piece of information, which is that for every individual loop, we get an EMF. So what happens if you start putting in more loops? Well, the effect on the EMF will change according to the number of loops. And each one of those loops can have a change in magnetic flux that passes through them. And well, that's the only thing that Faraday needed, was to incorporate the number of loops. That and one more thing. What Lentz found out was that when we change the magnetic flux in the coil, the induced current did not flow in the expected direction. It actually ended up flowing in the opposite direction of what was expected. And we'll talk about this a little bit more in the next video. For right now, we want to take this piece of information and we want to apply it to the equation that we have for magnetic flux. Because now we'll actually be able to see what happens when we change each of the individual variables inside of that expression. So we're just going to focus right now on the derivative portion. The n and the negative sign, we can always incorporate that later. But for right now, we just want to see how this expression will change with respect to time. The first thing that we should do is we need to evaluate what's inside the parenthesis. And inside that parenthesis is the dot product. A dot product is evaluated as the magnitude of each vector times the cosine of the angle between them. And so now we have to figure out, well, of everything inside the parentheses, what are we going to take the derivative with respect to? And you have your choice of those three. Let's start with choice 1. Let's change the magnetic field magnitude. So we are going to carry our derivative through the parenthesis set, but the only thing that's going to change is the magnetic field. Everything else will be left alone. Everything else will be treated as a constant. And so when we do that, we get derivative of magnetic field with respect to time times the area times cosine of the angle. So that would be the change in flux with respect to a changing magnetic field. The other way that we could change the flux is if we changed the size of the cross-sectional area of our coil, keeping everything else constant. So keeping everything else constant, the field magnitude remains constant, the cross-sectional area changes, and the angle relationship remains constant. So there's another way of representing the change in flux. Third way, change the angle relationship. So to do that, we keep the magnetic field constant, we keep the cross-sectional area constant, but now we have to look at the change in the angle with respect to time. That means we have to take the derivative of cosine theta. So what's the derivative of cosine? Well, derivative of cosine is negative sine. I'll bring the negative to the front. And there is our third expression. Technically, we'd have d theta dt out here. But these are going to be the methods in which we will be able to identify the induced EMF in a given circuit or in a given loop. And so each of these could now be set equal to the EMF if we applied a negative n to each of these expressions. Now I'm going to bring this video to a close here in just a couple of minutes, and we'll actually explore some example problems involving these three different situations. So we'll see what it takes to change a magnetic field, change an area, change an angle, etc. But what if we had more than one of these things occurring at the same time in a system? What if I had a changing magnetic field and I was rotating the coil? What if I was changing the size of the coil as the magnetic field was changing? So in those cases, how do we combine the three different methods of change in magnetic flux? Well, we do that by adding together the effects. And so the total change in magnetic flux for any system would look like this. All I'm doing is I'm combining the different methods in which magnetic flux for a system can change. One method, oops, forgot the dt here. One method would be change in magnetic field. Another is change in area. and then the third is change in angle. And what we do is, for any given moment in time, we look at the rate at which each value is changing, but then we have to use the instantaneous values of the other two variables when we evaluate this. Likewise, when we get to the second expression, I would have to look at the instantaneous value of magnetic field, the rate at which the area is changing, the instantaneous value of theta. For the third, we would have to look at the instantaneous values of field and area, the instantaneous value of angle, and then the rate at which that angle is changing. Now, this is not to say that we're going to have problems in our homework or a test where all three of these possibilities are occurring in the same problem, but in real life, it could happen. And we need to be aware of that as we move forward with our work. But if you have a system where the area of your coil is constant and the angle relationship between your magnetic field and your area vector remain constant, well, if your area is constant, then what does this derivative equal? It equals 0. So that second term is out. What does this derivative equal if you maintain a constant angle? 0. And so everything just breaks down to the first example that we saw, where only the magnetic field was changing. Well, what happens if nothing's changing? What happens if the area is not changing, if the angle is not changing, if the magnetic field is not changing? If nothing's changing, then what is the change in flux? Well, it's 0. And if you don't have a change in magnetic flux, you don't get any induced effects. And this is the real trick behind electromagnetic induction, is that we have to have a changing magnetic flux in the system. So that'll be the end of this video. When we come back, we will look at example problems involving specifically, individually, these three different methods. And then we'll start putting things together to see what happens when we have both a regular battery inside a circuit and this new invisible induced EMF that we're talking about here. So see you back for part 2.